So in an ideal transformer, we have lossless coils. Meaning that the resistance of the primary coil R1 and the resistance of the secondary coil R2 are 0 ohms. And we have perfectly matched coils. So that means that our mutual inductance term M is exactly equal to the square root of L1 times the square root of L2. So I'm going to draw a circuit that contains an ideal transformer. So on the left-hand side, we are going to have the source side of the circuit, which will be connected to our primary. So here's some voltage source Vs, terminals for said voltage source. And we've got our coil, L1. I'm going to put dot on the top, where we've got our secondary coil, L2. I'm also going to put a dot on the top. And we are going to note that these coils are perfectly matched to each other, such that we have an ideal transformer by using this pair of vertical lines. So whenever you see a circuit with two coils together and they've got a pair of vertical lines between them, that means treat this thing as if it is an ideal transformer circuit. Okay. Over on the right-hand side here, I'm going to affix some particular load impedance, which I'm just going to call ZL. Like so. And I'm going to indicate here on the figure that coil 1 has N1 turns and coil 2 has N2 turns, and you'll usually see this with a colon in the middle of it, which is going to be related to what's called our turns ratio, and I will define that in just a moment. So everything in this red box that I'm drawing right here is an ideal transformer. I'm going to define the voltage drop on my primary side as V1 like so, and my primary current is going to be flowing into coil 1. My secondary voltage is going to be V2, and I'm going to define my current I2 as flowing out of my secondary coil. So let's talk about what that implication of those directions of those currents are with respect to the polarities of the voltages that I've defined here. Okay? So the overall goal in this particular system is that our voltage source Vs supplies power through our transformer to this load ZL, right? So we have a source side and a load side, and the source is in some way, shape, or form supplying power to our load. So the primary coil is absorbing power from our source. And we can see that very specifically because our current I1 is flowing into the positive polarity terminal. So coil 1 absorbs power from our source. Then magic happens. It's no magic at all. It's actually just our transformer stores energy, as we learned in class yesterday. And then that energy, that stored energy, effectively gets delivered to our load. And if we look at things here, we can see that our current I2, as it circulates around this loop, is flowing into the negative polarity terminal, flowing out the positive polarity terminal. So energy stored on this side is what's delivered to our load. So we have a very simple system where effectively energy in equals energy out. Okay, so nothing wild or crazy here. Everything is obeying the law of physics exactly as we would expect. Yes, sir.
What did you say about the colons within look into?
So we're going to define this as a turns ratio here in a minute. So this will be expressed effectively as a fraction momentarily. But on a schematic diagram, you'll usually see just N1 colon N2, letting you know how many turns coil 1 has with respect to coil 2, or how many turns coil 2 has with respect to coil 1. So you might see it as something like 3 colon 5, meaning the coil on the right-hand side has 5/3 as many turns as the coil on the left-hand side. All right, so speaking of our turns ratio, so the inductance of a solenoidal coil is proportional to the number of turns in that coil squared, which you guys should have learned in your Physics 202 class, and you'll get way deeper into that when you take Electrical Engineering 411 this spring. You'll know more than you ever want to know about inductive coils by the time you get to 411. So we can say that L2 over L1, the ratio of the inductances, is going to be equal to N2 squared over N1 squared. And this is going to be our turns ratio A squared. So from this definition, our turns ratio A is simply going to be N2 divided by N1, which is the same thing as the square root of L2 over L1. I want to make an important note here. We have just defined the turns ratio in this class to be the ratio of the number of turns in coil 2 or our secondary divided by the number of turns in coil 1, our primary. This is how all circuit analysis textbooks do it. That being said, in industry, for whatever reason, they do exactly the opposite. And the turns ratio is defined as the number of turns in the primary over the number of turns in the secondary. Okay. So you, through the course of your internships and all of that kind of good stuff, you might hear people refer to the turns ratio as effectively the inverse of this thing. And all that's really going to do, as you'll see here in a couple of moments, is whenever I tell you to multiply, you should divide. Whenever I tell you to divide, you should multiply. I don't know where that disconnect came from. And if I had the forethought, I would have just updated my notes to be the industry practice, but I forgot about it until right now. And so I don't want to mess up all of the algebra in front of you guys. So I'm just going to teach it the way that I've been teaching it. I just want to make you aware of that. Okay. All right. So let's take a look at some things here. Okay. So my induced voltage, V1, using the laws that we've developed in class, what should this be? So think my positive polarity terminal is at the dot, and it looks like my current is flowing into the dot. So J omega L1, because we're dealing with phasors, J omega L1 I1. My positive polarity terminal is at the dot. My current I2 is flowing into the undotted terminal. So I should have minus J omega M times I2. Are we okay with that? So because our coils are perfectly coupled, we could replace this M by the square root of L1 times the square root of L2. But we can play around with things a little bit more. So let's look at a quick kind of identity, for lack of a better word. Okay. So if I have A times L1, that would be the square root of L2 divided by L1 times L1. Right? Anybody got any beef with that whatsoever? I could move this L1 inside of my square root sign, which would give me the square root of L2 times L1 squared over L1. And then this L2 squared would cancel out this L1 here in the denominator. And so A times L1 is just M for perfectly coupled coils. So I'm going to make this substitution. So that's going to give me J omega L1 times I1 minus J omega A L1 times I2. And I have a common factor of J omega L1 that I can now pull out of both of those terms, leaving me with J omega L1 times I1 minus A I2. Are we okay with that? So now let's write our induced voltage V2. Okay. So we have the positive polarity terminal of our voltage V2 is at the dot, and our current I2 is flowing into the undotted terminal. So I believe that's going to give us negative J omega L2 I2. I'm going to put it over here. For our mutual term, our positive polarity terminal is at the dot. Our current is flowing into the dot, so our mutual inductance term should be positive. So that's going to look like plus J omega M I1. So we already know that M can be written as A times L1. So let's play around with things yet again and figure out how we can write L2 in terms of L1. Okay, so we know that L2 divided by L1 is equal to A squared. So it seems to me like L2 is nothing more than A squared times L1. Okay. So let's put that over here as another thing that we kind of know, right? So L2 is just going to be A squared times L1. So if we substitute in that relationship, we're going to wind up getting negative J omega A squared L1 times I2 plus J omega A L1 times I1. Are we okay with the level of algebra that I've done? Nothing too wild or crazy. And now we have a common factor of J omega A L1 on both sides that we can take out. So we've got J omega A L1 times I1 minus A I2. Everybody follow my algebra here. Yes,
I
Patrick.
have J omega A squared in the second line. Is that just like, oh, wait, yes.
So the J omega A L1 came out, leaving me with negative A I2, which is where this guy comes from. The J omega A L1 came out, leaving me with just the I1, which is where that guy came from. Okay. So if I were to take the ratio of my two voltages, so V2 divided by V1, I would get J omega A L1 times I1 minus A I2 divided by J omega L1 times I1 minus A I2. And we can see that this bit cancels out, this bit cancels out, this bit cancels out, and we are literally just left with our turns ratio. So the ratio of the voltage on the secondary side of our transformer to the voltage on the primary side of our transformer is the exact same thing as our turns ratio, meaning that V2 is nothing more than A times V1 in an ideal transformer. And similarly, V1 is just V2 over A. Now, as it turns out, and I actually had to prove this to myself, if we change the direction of any of the currents, so if I1 is flowing in and I2 is flowing in, we'll get the exact same result for the voltage. If I1 is flowing out and I2 is flowing out, we'll get the exact same result for the voltage. If I1 is flowing out and I2 is flowing in, we'll get the exact same result. It's not until we're looking at the powers that our turns ratio is going to start messing with that relationship at all. And it's going to actually wind up showing up in the currents. So if the dots are on the same side and the positive polarity terminals are on the same side, our turns ratio is always just going to be V2 over V1. If our dots are on the bottom side, but they're both still on the same side, it does not change literally anything. So when the dots are on the same side and the positive polarity terminal is on the same side, we get A is equal to V2 over V1, 100% of the time. If we have dots on the opposite side of a transformer. So let's run through that really quickly here. Okay. So similar situation. We've got our source voltage Vs. Now we've got our ideal transformer. Our dots are on opposite sides. Here's our voltage V2. And I'll let you guys pick the directions for our currents because that's how little they matter. So I1 flowing in, I2 flowing out. Sure. Okay. So here's our situation. In this case, our voltage V1 is going to be J omega L1 I1 plus J omega M I2. Anybody got any problem with that? So let's make the same substitutions that we did the last time. So that's going to look like J omega L1 I1 plus J omega A L1 times I2 looks like J omega L1 times I1 plus A I2. For our voltage V2, positive polarity is at the undotted terminal, current's flowing into the dotted terminal. So the self term should be negative. So we'll have negative J omega L2 I2. For our mutual term, positive polarity is at the undotted terminal. I1 is flowing into the dotted terminal, so our mutual term should be negative. So we'll have negative J omega M times I1. And then using similar substitutions from up above, we have negative J omega A squared L1 I2 minus J omega A L1 times I1. So there is a common factor of negative J omega A L1 that I can pull out. So I'm going to have a factor of I1 here plus A I2 here. And we should very be able to see that the ratio of V2 to V1 in this case, where the positive polarity terminals are on the same side, but the dots are on opposite side, we get negative A. So effectively, I don't know why this is looking strange. There we go. If our dots are on opposite sides, or our positive polarity terminals are on opposite sides, we get negative turns ratio. Yes. So if our dots were on opposite sides and our positive polarity terminals are on opposite sides, so let me draw that really quickly because this will be the easiest way for us to wrap our head around. Okay. I'm just going to draw this as a quick sketch down here in the bottom right so that we can throw it away. So we've got a voltage source. So this is a situation that you just described, right? What's stopping me from literally flipping this circuit over on the right-hand side? Like literally just flipping it upside down, but maintaining every other relationship. Oh, all of a sudden I have the exact same case that I had at the beginning, where the dots are on the same side and the positive polarity terminals are on the same side. So it's case one that we already talked about. Does that make sense? Yeah.
Is there anything physically different in the oil?
Completely and utterly arbitrary. So it's where we're measuring the voltage is positive polarity with respect to negative. There, it is a section of wire wrapped around a chunk of metal. The coil doesn't care. Yes. So technically, from a practical sense, nowhere. They cannot exist because all wires have some amount of resistance. That being said, most transformers or magnetic circuits that are designed to be a transformer actually come pretty darn close to behaving like an ideal transformer. As a matter of fact, the practical transformer model, where we are attributing for the losses in our coil, the losses caused by, so it takes energy to magnetize a medium, even a ferromagnetic medium that magnetizes very easily. We lose some energy to heat there. We're going to get phase shifts due to rapidly magnetizing and demagnetizing the material, because this is going to be set up with an AC system. Anyway, the equivalent circuit model for a practical real world transformer contains an ideal transformer. That's the part that handles the, you need to step the voltage up or step the voltage down, you need to step the current up or step the current down, all of that kind of stuff. So this is really a tool that's used in more complex classes to model how a real transformer behaves. We just add the mechanisms that make it practical as external components in the forms of resistances, inductances, and capacitances where appropriate. So this isn't just, oh, I'm giving you an ideal case to play around with. This is how we treat real transformers. We just add the other components where we need. Okay, so I've answered a couple of questions here. So where things get kind of, sort of ish difficult is figuring out what's going on with our currents. Okay. And it's not really difficult at all. We just have to pay attention to what's happening. Okay. So I mentioned earlier that energy in should equal energy out, or power in should equal power out. But that was specifically when we had our currents defined like this, which there's nothing remotely wrong with this. We could choose other things, but we need to understand what's going on in the system, right? This coil is absorbing energy from this guy. This coil is supplying energy to this guy over here. So effectively, whatever power we have absorbed on the left-hand side should be supplied on the right-hand side. And if the direction of our current is wrong for the type of power that we're looking at, then that's going to slightly mess up our current ratio because we got one of our directions wrong or one of our polarities. So that's really the only thing that we have to pay attention to. So just to look at things here really quickly, and we can kind of do this as a very quick aside underneath here. Okay. So the complex power absorbed by coil 1, let's call that S1. Okay. So using just our fundamental definition of, complex power, what should that be? So VI conjugate, but because we're dealing with phasors instead of RMS phasors, we need to throw in that factor of 1/2, right? So 1/2 V1 I1 conjugate. Okay. S2, this will be the power supplied by coil 2. What should that be? (1/2 V2 I2 conjugate, right? Because this current is entering the negative polarity terminal. We know that these two powers should be equal to each other in a system in which energy is conserved, which is any real system, right? So I can say that 1/2 V1 times I1 conjugate is equal to 1/2 times V2 times I2 conjugate the 1/2s cancel each other out. And so I could rearrange this kind of slightly. So I could say, let's put V2 over V1 on this side. That would be the same thing as I1 over I2. I conjugate both sides, but V2 over V1 is A, which is just a real number. So what's the complex conjugate of a real number? The number itself, there, right? So 5 plus J0's complex conjugate is still 5 plus J0. So these conjugate signs don't actually matter at all. So this definition of our turns ratio was for this particular circuit with related to currents, but on the other one, we have to pay careful attention to, like I said, power in on the left-hand side versus power out on the right-hand side to make sure we give our current ratio the right sign. But the key thing to take away from this is if our turns ratio is a positive quantity, meaning N2 is greater than N1, then our voltage across our secondary coil will be larger than the voltage drop across our primary coil, right? So we are stepping up the voltage across the transformer. We are also, according to this relationship, stepping down the current. So we can't step up both the voltage and the current simultaneously. We'd be creating energy if we did. So if we step up the voltage, we have to step down the current in order to make the total power and energy the same. If we step down the voltage, we step up the current in order to make the total power and energy the same. Okay. So why are transformers used? Based on this piece of information. Why are transformers an integral part of any power distribution system?
It's easier to send electricity across transmission lines at high current, but you have to connect to low voltage to be able to separate.
Exactly opposite. So we step up the voltages really, really high on the order of hundreds of kilovolts so that the current is really, really low, because we know that losses are associated as I squared R losses in our lines, right? So the resistance of the wire isn't going to change if the voltage across it is a very large voltage or a very small voltage. But if we can make the current really, really small, the voltage drop across the line will be really, really small, or it will have less losses in it. So that's where we use transformers, or why they're so integral to power distribution systems. So at a electric utility plant where they're generating power, they might only generate at something like 20 kV, but they'll RMS, but they'll step it up to several hundred kV to transmit that power over very long distances, and then step it down 1 or 2 or even more times to bring it to the consumer so that we get just the 120 volts RMS that we're used to. Okay. So, all right. So we've talked about turns ratio and all of that kind of good stuff. I think I've done a good job of explaining that you need to be really careful with polarities and directions of currents and all of that kind of stuff to make sure that for when you should use A or when you should use negative A. So let's talk about some other interesting things, or at least I find them interesting. You guys will probably be pissed off, but that's okay. So I want to find the Thevenin equivalent circuit of a transformer. So let's say that I have the following system. So I've got some source voltage VS1 and some associated impedance Z1. So this will be our primary impedance. Connected to an ideal transformer. And for simplicity's sake, I'm going to have the dots on the same side. Here is my voltage V1. Here is my current I1. Over here, I've got my secondary. Here is my voltage V2. Here is my current I2. And we have N1 colon N2 down here. Then on the secondary side, I'm going to have another impedance. And just so that we understand what's going on and how we can apply this in various situations, I'm going to put another voltage source on our secondary side. And put a line over this so that we understand its phasor. And I'm going to label some terminals real quick. So this will be A, B, C, and D, like so. So for this particular configuration, we just learned a moment ago that the ratio of V2 to V1 should be equal to A, and that would be the same thing as the ratio of I1 to I2. So if A is a positive quantity, V2 is greater than V1, and I1 is less than I2. Okay. So what I want us to do is to find the equivalent circuit seen by this practical source on the left-hand side first. Okay. So we're going to disconnect that practical source on the left-hand side and find the Thevenin equivalent of this network. So everything to the right of terminals A and B. So I'm going to draw everything to the right of terminals A and B, like so. So here is one coil. Here's my second coil. Here's my voltage V1. Here's my current I1. Here's my turns ratio N1 to N2. Here's my impedance Z2. Here's my voltage VS2, like so. Plus minus V2. Here is I2. Okay, so if we want to find our Thevenin voltage, so let me make a note over here. So we are first finding VTH with respect to terminals A and B. So if I want to find my Thevenin voltage with respect to terminals A and B, what's the voltage that I'm actually looking for? Voltage between A and B, which is the same thing as V1, right? So I'm just going to put an equal sign over here and call this VTH A comma B. right? Whenever we're finding the Thevenin equivalent voltage, it's always the voltage drop across an open circuited set of terminals. A and B are already open circuited terminals, so all we're really looking for is this voltage V1. Okay, so I want you guys to use some high-level circuit analysis here and tell me what the current I1 is in this circuit. It's 0 because no current flows through an open circuit. Great. So if I1 is equal to 0, what does this imply about I2? It's also 0. Can't be anything else, right? If we step up 0, it's 0. If we step down 0, it's 0 because 0 times A is still 0. So our secondary current has to be 0 in this case. All right, so if our secondary current is 0, what is our induced voltage V2? I disagree. VS2. So there is no drop across this impedance Z2 because there is no current flowing through it. So Kirchhoff's voltage law tells us that V2 is equal to VS2. Are we okay with that? Oops. Okay. So now we can use our turns ratio relationship for our voltages to figure out what V1 is, since V2 is a known quantity. Okay. So what should it be? So is it going to be times A or is it going to be divided by A? Okay. So move V1 up here, move A down here. So V1 is V2 over A. Is equal to VS2 over A. Okay. We all okay with how we just found our Thevenin voltage? And I'm going to make a note out here. So this is V Thevenin A to B. We just used it. So if I1 is equal to 0, then that has to be equal to A times I2, right? So 0 is equal to A times I2 implies that A2 must also be 0. Then we have V1 is equal to V2 over A. Are we okay? Okay. All right. Now let's find the Thevenin equivalent impedance, seen looking in between terminals A and B. Maybe it would be better if I wrote this as this equals A and this equals A as kind of two separate things. Maybe that'll help you wrap your brain around it. All right, so ZTH, A and B. So how do we find the Thevenin equivalent impedance of a network? We need to be looking at a dead network, which means we're going to have to turn our voltage source VS2 off. And
That's really about
it. All right. So we are going to have this thing right here. This is still going to be defined as our voltage V1. This is still our current I1 for what it's worth. Let's put Z2 over here. So here is V2. And here is, excuse me, I2. So we've got this pesky transformer thing in the middle. And then we've got this impedance. And we don't really know what the impedance of the transformer is per se. So I think that we can apply a test source method to this network in order to determine what the impedance is looking into these terminals. Does that seem fair? So we're taking the same approach as we do when we have a dependent source, just because we don't really know what the impedance of that thing is, but we know if I can figure out the voltage drop across the terminals and the current flowing into the terminals, the ratio of those two things has to be the impedance. All right, so let's throw a test source over here. And let's just call this V test. And so we're looking for I test, and our Thevenin equivalent impedance will just be the ratio of V test to I test. So we can say that our Thevenin impedance, ZTH, seen between terminals A and B, is just going to be the ratio of V test over I test. Which is the exact same thing as the ratio of V1 to I1. Are we okay with that? Well, we can express V1 in terms of V2, and we can also express I1 in terms of I2. Okay, so V1, if we look up here at our simple relationships, V1 should be V2 divided by A. Are we in agreement with that? I1 should be I2 times A. Are we okay with that? So I'm going to make this look a little bit better. So I've got a V2 over A divided by an I2 times A. So I think that looks like V2 divided by I2. And that's multiplied by a factor of 1 over A squared. Are you guys okay with that? What's V2 divided by I2? My impedance Z2, by definition. So the Thevenin equivalent impedance is just my secondary impedance divided by a factor of A squared. So if I want to reflect my secondary impedance over to my primary side, I divide by a factor of a squared. So putting these two results together, I would have the following network, right? So here's my original VS1. Here's my impedance Z1. Here's terminal A. Here's terminal B. Then I'm going to have this impedance, which I'm going to call Z2 prime. And this impedance, excuse me, this voltage, VS2 prime, where this prime designation, I'm using a single prime to say I'm reflecting this to the primary side. VS2 is just, excuse me, VS2 prime is just VS2, dang it, I don't need the extra prime there, over A, and Z2 prime is just Z2 over A squared. So I've reflected everything from my secondary side over across my transformer, and I'm left with just an absolute joke of a circuit to analyze. What do you think would change if I was trying to reflect everything to the opposite side? Or effectively, if I was trying to find the Thevenin equivalent circuit with respect to terminals C and D. Everywhere I divided by A, I'd multiply by A. Everywhere I divided by A squared, I'd multiply by A squared. All right, so how are we feeling about this stuff? Hayden, how may I help you?
When you say reflected, is that what you mean by that?
So if we look at our equivalent circuit here, there is no longer a transformer that exists in this circuit. Everything that was over here has been moved to the and connected directly to the primary terminals of our transformer. So we reflected everything from the secondary over to the terminals of the primary side, which were A and B. And just to spell it out super obviously, going the opposite direction, we would have VS1 double prime in series with Z1 double prime. Here are terminals C and D. Z2, VS2, where VS1 double prime is A VS1 and Z1 double prime is A squared Z1. So all I mean when I say reflecting is just moving stuff to the primary side or the secondary side. So if we reflect the secondary over to the primary, we have this guy. If we reflect the primary over to the secondary terminals, we have this circuit. To let me know the 2' so that they're going to the second area. One prime to go to the primary. Okay. So we've got a couple of minutes left here. I'm trying to decide whether or not we have enough time to look at auto transformers. I know that we for sure don't have enough time to look at 3-phase transformers today, so I think we're going to knock off a little bit early, and we're going to wrap up transformers on Monday. So I want to be clear here. You guys should expect, I believe, one more homework on this transformer material. So the next thing that I give you guys will be related to what we did in class on Wednesday and what we did in class today. I don't know exactly that I'm going to give you a homework assignment related to auto transformers. They're an interesting thing and they're definitely used in industry, but as a very, very brief thing, an auto transformer is what you get when you have a single coil, but you tap it in multiple locations so that you have the same flux flowing through different parts of the same coil. And you can make that behave like a transformer as well. A three-phase transformer is just three single-phase transformers tied together in either a delta or Y configuration. So it's harder to draw the damn thing than it is to actually understand what's going on. So we're going to wrap those kind of things up on Monday, and then we will be moving on to bigger and better things, which I can't actually remember what they are just yet because I haven't looked at my notes. I'm going to sign that homework today. I hope to go up to my office and get it posted here in the next several months. Yes, I'm aware of it, but if you don't have it in hand by Sunday, text me.
When's the soonest you can post?
What?
When's the soonest you can post it?
I'm going to try to get this up this afternoon. So all of this prime, so this prime right here just means the original thing reflected over to the primary side terminals. And this double prime means primary stuff reflected over to the secondary side terminals. That's it. So it's not a derivative or anything like that. It's just a designation of, did I send that information to the primary side or did I send that information to the secondary side?